Okay, so let's get started. So we have Ethereum as the sending chain, and we have Near as the receiving chain, and we have the relay in the middle. Now, in a typical bridge, any transactions that happen on each side, the relay reads them, and then the relay makes a transaction to the other side inside the smart contract on Near. Uh, and the only guarantee that this smart contract has about the validity of this transaction is that the relay has signed it. And in this situation, obviously, we are dependent on the relay. Now, in Electron protocol, we remove the security dependency on this relay, and let us see how we do that. Now, in order for this smart contract to be able to independently verify this transaction without relying on the relay, uh, we basically need to prove to this smart contract on Near that this transaction was included in the Ethereum mainnet blockchain. What do we mean by that? That this transaction was included inside a block, and that block is actually part of the Ethereum canonical chain. So if we can somehow show that this transaction was included in the Ethereum blockchain, then we don't need to rely on the relay signing off on the transaction. So how do we do that? Uh, so the process for that is quite simple. We basically verify the Ethereum consensus. And how do we do that? We basically check that the validators of Ethereum mainnet, that Ethereum validators have signed off on a block that contains this transaction, right? So the relay basically needs to send across uh, not just the transaction but also the validator signatures now, right? Earlier it was just sending the transaction and its own signature. Now it will send the validator signatures, and they then need to be verified along they then need to be verified inside the Near smart contract. And if total 67% of the voting power, if the signatures corresponding to 67% of the voting power on Ethereum mainnet validate, then we know that the transaction is actually valid and was included in the Ethereum mainnet, right? Uh, so we call this security layer one, right? Where now what do we mean by that? So basically now, if an attacker wants to send a invalid transaction across this bridge, they would need to convince 67% of the Ethereum mainnet validators to sign off on a fake transaction and send that across the bridge, right? So the relay cannot do anything. They have to convince 67% of the Ethereum validators. So we call this security layer 1, where 67% uh, validator collusion is required, right? Uh, okay, great. Um, okay, great. Uh, Now let us say our bridge becomes very big and it has $1 billion worth of TVL, right? Now suddenly $1 billion is a massive bounty, and it is enough incentive for someone to actually put in the effort to convince these 67% validators, right? It makes sense for these guys to come together, because if they do that, then they can make $1 billion. So how do you prevent against this kind of an attack in the situation that where the Ethereum validators have decided to attack our bridge? So in our bridge design, as you can see that the relayer is not signing off on the transaction, which allows us to have multiple relayers. In our network, we have a permissionless relayer system where anyone can become a relayer. Now, what will happen is that uh, since these Ethereum validators will essentially sign off on a block, so which actually does not is not part of the Ethereum mainnet, but they have only signed off on that block just to submit that to the Ethereum to the bridge in order to hack it. So now the problem is that there are so many relays in the network, and one of those relays will also what's the actual honest transaction on the honest the real block on the Ethereum mainnet and send that across. So let's say the attacker is able to uh, uh, let's say convince all the relays in the network to send the only the fake blocks across. But even if there is just one honest relay, even if there's just one honest relay, then that will send the honest the real block on the other side, and the smart contract will essentially have two different blocks at the same height. So let's say it was at height h at this point. Now it will receive two different blocks that are at the same height, and the smart contract is going to know that something fishy is going on, and it can basically respond appropriately and maybe halt the bridge, right? So we call this security layer two, where 100% relay collusion is required, and even if one relay is honest, uh, then the bridge basically responds. Now, uh, now there's a problem here. Uh, since what happens if the transaction that came from the honest layer is too slow to reach the smart contract, and the malicious transactions makes through to the smart contract before. In that case, the money will be lost, and the fake block will make to the bridge before the actual block, and the bridge would be too late to respond to that. So how do we solve this problem? So this is where security layer 3 comes in. So what is security layer 3? In security layer 3, we basically rely on a security feature provided by the Ethereum consensus itself, and that security feature is called slashing. We have all heard of it. So in slashing, uh, so let's see what slashing is, right? So let's say validators are currently the blockchain is currently at height edge, and what happens is that some validators collude together and sign off on two different blocks at the same height, right? They sign off on two different blocks on the same height, and this is basically considered a slashable offense, because in this case it's quite clear that the validators are trying to come together to attack the network, or maybe if the one of these blocks is a malicious block, right? In that case also this is a slashable offense, right? So now what the attackers will essentially try to do in order to hack the bridge is that they will create a block that they never broadcast to the Ethereum mainnet, and only this block basically gets added, and this block is specifically created for the purpose of submitting to the Electron bridge in order to hack it. Now, in this situation, what will happen is that Ethereum mainnet will continue to build on this chain, but this particular block will get submitted to the bridge, and the bridge would be hacked. But what happens now is that in order to do this, the validators have essentially signed off on two different blocks at the same height, and since this malicious block, this doubly signed block rather, has been submitted to the Ethereum smart contract, uh, somebody, this honest relay, can basically pick up this doubly signed block and submit it back on the Ethereum mainnet, and this will tell the Ethereum mainnet that these validators have essentially done double signing, and they will basically get slashed on the Ethereum mainnet. So if validators were to try and they collude together and attack our bridge, they would get slashed on the Ethereum mainnet. And the coolest thing about this is that the Ethereum consensus penalizes these kind of large coordinated attacks quite badly. And basically, to give a rough estimate, these 67% validators will essentially lose almost all of their stake on Ethereum. And if, let's say, the total amount of money staked on Ethereum is $15 billion today, then $10 billion of the stake would be lost. And since this amount is basically greater than the TVL of the bridge, which is $1 billion, we know that this bridge is secure. So this is called security layer 3, which is called validator slashing. So basically, our bridge is over here is essentially borrowing the entire economic security of the Ethereum mainnet, because in order to hack the bridge, you have to hack the Ethereum mainnet, and we can say that our ZK bridge uh, has the same security level as a ZK rollup. Uh, and Yeah, so that's sort of the overview here. And just coming back to security layer, layer 2 back over here, again, it's very important in this network that at least one relayer is honest, so that that relayer can basically act as a fisherman to to see any transactions that have been submitted by the relayers that are essentially malicious headers, and can do basically reporting of those malicious headers back to the Ethereum mainnet. So if you have at least one honest relayer in the network, then we can be sure that somebody will be able to trigger slashing on the Ethereum side. And the reason we can assume this is because, first of all, anyone can become a relayer. So let's say the smart contract liquidity was being used by, let's say, some large DeFi protocol. In order to ensure the security of the bridge, they can start running a relayer. And since they know that their relayer is honest, they basically know that the entire bridge is honest. Uh, Similarly, like even if like this is not even required by the relayer, anyone can basically look at this data and send it across. Like somebody could actually run just a fisherman node, not even a full relayer, where they're just constantly watching for these kind of events. And the reason it makes sense to do it is because basically this kind of slashing reporting is highly rewarded, and anyone who does slashing reporting is actually wins a part of the amount of stake that is burnt for the attacking validators. So it's basically this kind of fisherman activity is kind of rewarded also. uh, and again, well, like we can assume that somebody will send it across. uh, so that's the overview of security in Electron protocol.